Okay, so welcome to the course on electric and hybrid electric vehicles. See, in the past few lectures, we have gone through the computation of different performance parameters of electric vehicles, like how we will be able to convert the speed from kilometer per hour to meter per second, or if we are available with some RPM and radius of the wheel, then how we will be able to calculate that particular speed as well as power, right? Then we have gone through the various equations of dynamics of vehicle, where we have seen the total three different resistances opposing the flow of the vehicle. Okay, and that was aerodynamic drag, rolling resistance, and gradient resistance, right? And then you also need know how to calculate the torque. Okay, then yesterday we have started with some important task, that what is the force required to reach maximum speed in certain time t seconds. Suppose I have a vehicle and it needs to be reached at 25 kilometer per hour speed in say 10 seconds. Okay, so during to get this, to meet this target, what will be the force required, what will be the power that will be consumed from by the battery, right? So this depends, the answer depends on how this acceleration takes place, right? And we have discussed the constant linear acceleration, right, where we are following this graph. Okay, starting from 0, I have constant acceleration until we reach the maximum speed vf in time t. Okay, let this acceleration be a, right? So that was the accelerations which we have considered, right? And we have derived various equations of this acceleration. Say a is equal to maximum speed divided by time t, right, where vf is in meter per second and time is in second, right? Then from the knowledge of this acceleration, we will be able to calculate acceleration force, which is nothing but m into a kg into meter per second square, right, where m is nothing but the mass of the vehicle in kg, right? So that was the force required. Now in this particular, when this much amount of force is applied at that time, our vehicle will travel certain distance. Okay, and that distance s was given by 0.5 at square. Okay, and from this distance we will be able to calculate the work done w, and that was equal to acceleration force multiplied with the distance. Okay, so if you put the values, we will get w is equal to half m into vf square. Okay, so that was the work done by the vehicle, and from this knowledge of the work done, we will be able to calculate our two parameters, which is the average power. We are talking about the acceleration power. Okay, so average power is given by work done upon time, and it is equal to half m vf square by t. And if we talk about the peak power, then peak power is given by m into vf square by t. So we have seen this scenario. Okay, so whenever we assume the constant linear acceleration of any vehicle to reach the maximum speed in time t seconds, at that time whatever amount of average power required, the peak power required will be double of that. Okay, so motor needs to generate very high amount of torque, and that is what we have seen in the example which we have considered yesterday. Okay, so for two wheeler there was not any problem, but whenever we consider the four wheeler, at that time we have seen that if my speed is 50 kilometer per hour and it has to reach this value in 20 seconds, then the torque required by the motor is 258 newton. Okay, and that requires the peak power of 11.58 kilowatt. Now if I increase my speed to 70 kilometer per hour, then the peak power required was 23 kilowatt. And if I further increase the speed to 90 kilometer per hour, then the peak power required was 37 kilowatt. Okay? So we have assumed here that we should avoid doubling the peak power by reducing acceleration as speed increases. Okay, so if we increase the speed at that time, if you are able to decrease the acceleration, then the highest power, the peak power required will be less, and it will consume less amount of energy. And that is why we came up with another alternative in which we are doing, what we are doing is, whenever the speed is low, at that time we are accelerating at a high rate. Okay, so up to time t by 2 my acceleration will be high, and after half time we are decreasing the acceleration as speed is increasing. Okay, so that was our second alternative. So first part of acceleration was a1 by 2, and second part, sorry, first part is a1 and second part is a1 by 2 times acceleration. Okay, so what we are doing, we are accelerating the vehicle at a rate a1 for first t by 2 time, and at a rate a1 by 2 for the time, rest of the time, that is from t by 2 to t. And what we have seen is, we have seen that acceleration a1 required in this case was equal to vf minus v0 into 4 by 3 times t. Okay, so what we can see, what we can conclude here, that the power required at time t will be 0.667 of that for the linear acceleration case. Okay, so in this case, whenever we assume the constant linear acceleration, at that time the power required will be high compared to this type of acceleration. Okay, so if we accelerate our vehicle in such a way that for first half time we are accelerating at high value, and for rest of the time we are accelerating at half of the initial acceleration, and that will consume 0.667 less power compared to constant linear acceleration. Okay, so that is what we have seen, and we have seen the simple example of a two-wheeler and a car. Right, now let us try to consider some more examples for both the cases, and then we will compare these two matters. Okay, so we have been available with the vehicle. I am talking about the two-wheel. Okay, so for the vehicle given below, compute total traction force, compute total traction force assuming pickup from assuming pickup from say 0 to 50 kilometer per hour, 0 to 50 kilometer per hour in 20 seconds. Okay, then you need to calculate power as well as torque at three different values: 30 kilometer per hour, 50 kilometer per hour, and 80 kilometer per hour. Okay, so for this example you have to assume linear acceleration and let our slope be 0. Okay, so assume linear acceleration and zero slope. Okay. So motor parameter, wheeler parameters are given to us. Say right now I have, okay, first we'll take the type of vehicle. Then gross vehicle weight in kg is given to you. Drag coefficient of front area in meter square. Rolling resistance and radius of the tire. Okay. So consider two-wheeler first. Okay. The gross vehicle weight is 200 kg. Drag coefficient is 0.9. Up frontal area is 0.6 meter square. Rolling resistance coefficient is 0.015 and radius is 0.28. Okay. Then we have three-wheeler also and four-wheeler also. Okay, so three-wheeler is having data 600 kg, CD is equal to 0.5, area 1.6, coefficient 0.05, radius is 0.2, and for four-wheeler it is 1500, 0.3, 2.5, 0.015 and 0.3. Okay, so these are the data given to us. So what we will do, we will calculate for this two-wheeler and remaining two vehicles I will left it for you as an home assignment. Okay. So after completion of this lecture, whenever you got time, just try to calculate the same data for three-wheeler also and four-wheeler also. So we have been given this much amount of data and we need to calculate the total traction force, assuming the pickup from 0 to 50 km per hour in 20 seconds. Then you need to calculate the power as well as torque at three different speeds: 30 km per hour, 50 km per hour and 80 km per hour. Right? So now the first thing is I need to know my acceleration. Okay, I need to reach 50 km per hour in 20 seconds. Okay, so at what acceleration value I need to accelerate the vehicle? Okay, I need to know what should be my meter per second square, acceleration in meter per second square. Okay, so we'll start computation. So we are considering two-wheeler. Okay, so first thing is acceleration. Now we know very well how to calculate the acceleration. Acceleration is nothing but differentiation of velocity with respect to time. Okay, and velocity is given to you 50 km per hour. We need to convert it into meter per second. Okay, so 50 by 3.6 and initial velocity we are assuming as 0. Okay, so this will be my answer and difference in time will be 20 minus 0. Okay, so answer we will get is 0.694 meter per second square. Okay, so this is the amount of acceleration. Okay. Now we know one equation of velocity v. Okay, so if you know the velocity v, then it is given by u plus at. Right. So what is u? U in our case would be equal to 0. Initial velocity is 0. So my equation will now reduce to 0 plus 0.694 t. Okay. So this is our equation of interest. Now we need to calculate the total traction force, right? So if we write down the equation for total traction force, Ft, then it comprises of acceleration force plus aerodynamic drag plus rolling resistance plus gradient resistance. Okay, this is my equation. But as if you read the data carefully, then the slope we need to assume is 0. Okay, so this gradient resistance will become 0 as it is given by mg times sine alpha. Okay, so sine alpha, sine 0 will become 0. So we did not need to calculate the gradient resistance in our case. Okay. So now the resistance of our interest is acceleration force, aerodynamic drag and rolling resistance. Okay, so let us start with the aerodynamic drag. We know the equation of aerodynamic drag very well. Aerodynamic drag, let us say FD is given by half rho CD A times V square. Okay, where rho is air density and it is equal to, yes, it is equal to 1.2 kg per meter cube, right? Then CD is drag coefficient, which is already given to us. Of frontal area A is also given to you and velocity is also given to you. Now this time velocity for us is total 3 velocities are there: 30 kilometer, 50 kilometer and 80 kilometer per hour. Okay, so we will keep this V as it is. Okay, initially what we will do, we will try to find out the common equations and then we will put the values of V for 3 different values. So you will be able to calculate total traction force required. Okay, so put the remaining data. We will get half into 1.2 into 0.9 into 0.6 into V square. So the aerodynamic drag FD is nothing but 0.324 V square. Okay, this is about the aerodynamic drag. Now let us try to compute second resistance, which is rolling resistance. Okay, so rolling resistance FR is given by mg mu cos theta, right? But we eliminate the use of cos theta because the maximum gradient practically we will find is around 10 to 12 degree, and for that this cos theta value is nearly equal to 1. Okay, so we generally ignore this cos theta and our rolling resistance equation is reduces to mg times mu, where m represents weight of the vehicle in kg, g is acceleration constant 9.81 meter per second square, and mu rolling resistance is given to you, coefficient is given to you 0.015. So ultimately we will be available with 29.4 Newton of rolling resistance. Okay, as we have discussed, this rolling resistance and gradient resistance are independent of the velocity. Okay, then we are left with the acceleration force, right? So acceleration force let us say FA, it is given by m into A. Okay, so A is dv by dt, which is already calculated by us. It is equal to 0.694 and that is equal to 138.8 Newton. So we have all these three values. Okay, let us say these values 1, 2 and 3. Okay, and total tractive force required according to this equation A is summation of acceleration force, summation of aerodynamic drag and summation of rolling resistance. Okay, so let us try to find out the total force Ft equal to Fa plus Fd plus FR. Okay. FA is 138.8 plus FD is 0.324 V square. 0.324 V square plus rolling resistance is 29.4, right? So we will be available with 168.2 plus 0.324 V square. So this is the generalized equation of total tractive force required to reach 50 km per hour in 20 seconds, right? Now what we need to do is, let us go back to the data. We need to calculate the total traction force, power and torque at three different velocities: 30 km per hour, 50 km per hour and 80 km per hour. Okay, so let us consider now 30 km per hour first. Okay, so at 30 km per hour, okay, so if we convert this kilometer per hour into meter per second, then we will get 8.33 meter per second, just 30 divided by 3.6. Okay, so this is our meter per second. Now what will be the time for this particular case? Okay, to reach 30 kilometer per hour with the acceleration of 0.694 meter per second square, we will require how much time? Okay, so we know this equation, v is equal to 80. Now time t is equal to v by a, where v is 8.33 divided by acceleration is 0.694. So ultimately the time will be 12 seconds. Okay. So in this 12 seconds we will reach our 30 km per hour speed. Okay. Now what is the force required? Ft will be equal to 0.324 into v square, that is 8.33 square plus 168.2, which is equal to 190.68 Newton. Okay, so this is the total force required. Okay, then we need to calculate torque. So torque T is equal to force multiplied with the radius. Okay, so R tire, right? Force is, just we have calculated, 190.68 Newton into tire radius is 0.28 meter. Okay, and that comes around 53.39 Newton. Okay, so this much amount of torque is required to produce this much amount of tractive force. Okay, and to generate this much amount of torque, what should be the power required? The power is nothing but force multiplied by velocity v. Okay, and that should be equal to 1.587 kilowatt. Okay. So these are the required data at 30 km per hour, assuming constant linear acceleration. Okay. Now let us increase the speed and let us see what happens to the torque and power requirement. Okay. So consider the second case at 50 km per hour, which is equal to 13.89 meter per second. Okay, and of course if you calculate the time required will be equal to 20 seconds, right? So the total traction force required will be equal to 0.324 into 13.89 whole square plus 168.2, and that is equal to 230.6 Newton. Now you can see the tractive force required is increasing with increase in the speed. Okay, and the torque required is 64.56 Newton meter. Okay, here the unit should be Newton meter. And the power required is tractive force into velocity v. It is equal to 3.202 kilowatt. So to reach 50 kilometer per hour in 20 seconds, if my velocity is 30 kilometer per hour, then I will require 1.5 kilowatt of power. And if my velocity increases to 50 kilometer per hour, then I will require the power 3.2 kilowatt. Okay, so power is increasing as we are increasing the speed, right? And then the third case, where my speed velocity is 80 kilometer per hour. Okay, so we have 22.22 meter per second. What will be the time? Time is equal to v by acceleration. So it will take 32 seconds to reach 80 kilometer per hour. Okay, so the force required to reach this value is 0.324 into 22 into 20 square, 22.22 square, 168.2, and that comes around 328.17 Newton. If I talk about the torque, torque is equal to Ft into R will. Okay, so 328.70 into 0.28, which is equal to 91.88 Newton meter. Okay. And to generate this much amount of torque, the power consumed is given by Ft into V, which is equal to 7.291 kilowatt. So these are the values of the power required if we assume the constant linear acceleration. Okay, so first kind of acceleration, the type of acceleration we are considering is constant linear acceleration, right? Now if we assume the acceleration of this kind, that means for first t by 2 second my acceleration would be a1, and for next t by 2 second acceleration would be half of that of a1. In that case, what will be the force required and what will be the value of power and torque? Okay, let us try to calculate this thing and let us see what happens, which particular type of acceleration is advantageous to us. Okay, so we have another data now. Say you need to assume vehicle acceleration is some value of first half time, that is 10 seconds, and half as much for next half time, that is next 10 seconds, to still reach same velocity, that is 50 kilometer per hour in 20 seconds. Now again you need to compute traction force, power, and torque at 30 kilometer per hour, 50 kilometer per hour, and 80 kilometer per hour. Okay, so we'll consider only single case of 50 kilometer per hour. Okay, so V equal to 30 kilometer per hour and V equal to 80 kilometer per hour. These two velocities you have to calculate yourself. Okay, so this is our home assignment. Okay, you have to carry out the same problem with these two velocities, 30 kilometer per hour and 80 kilometer per hour, and we will try to calculate it for 50 kilometer per hour. Okay, so it is given some case. Okay, so let us assume this particular thing. Okay, so let A be the acceleration for first 10 seconds. Okay, and V1 the velocity, V1 the velocity at the end of 10 seconds. Okay, and A by 2 is the acceleration for next 10 seconds, for next 10 seconds, and V2 is the velocity at end of next 10 seconds, that is 20 seconds. Okay, so talking about the velocity V1, now velocity V1 is 80. Okay, initial velocity is 0, so V is equal to U plus 80. U is 0 in this case, and A is equal to acceleration, and time is t. Okay, so V1 will be equal to 10 times A, and V2 will be equal to V1 plus 10 times acceleration is A by 2. Okay, so ultimately we are left with V1 plus 5A. Okay, so these are the values of two velocities, V1 and V2. Okay, so now we know V1 is equal to 10A, right? So put these values in equation of V2. Now we have equation of V2 is equal to V1 plus 5A. So V1 is equal to 10A plus 5A, that is V2 is equal to 15A, and from this acceleration A is equal to V2 divided by 15. Okay, and what is V2? V2 is my final value. What is the final value? Final value is 50 kilometer per hour. Okay, so just convert it into meter per second and divided it by 15. We will get 0.926 meter per second square. Okay, so this is our acceleration. Okay, so initially for first 10 seconds we will accelerate our vehicle at 0.926 meter per second square, and after that half of that for next 10 seconds. Okay, so for this much amount of acceleration, now let us try to calculate the traction force required, right? So we know that traction force required is acceleration force plus aerodynamic drag plus rolling resistance. Okay, gradient resistance we need not to consider, as the grade is given to us 0. Okay, so Fa is equal to Ma plus Fd half rho Cd Av square plus mg into mu. Okay, We are available with all the values. Okay, so put these values. Okay, I am considering the case of two-wheeler. Okay, so velocity 50 kilometer per hour, that is 13.89 meter per second. Okay, for a two-wheeler, let us say velocity v is equal to 13.89 meter per second square, and acceleration would be a by 2, and this is equal to 0.463 meter per second square. So now calculate the aerodynamic drag Fd. Okay, so aerodynamic drag Fd is given by 0.5 into 1.2 into CD is 0.9, area is 0.6, and velocity is 50 kilometer per hour, that is 13.89 meter per second square, and this comes around 62.51 Newton. Okay, if we talk about rolling resistance Fr, it is equal to mg times mu, where m is 200, acceleration constant is 9.81, and rolling coefficient is 0.015, and that comes around 29.43 Newton. Okay, and then acceleration force Fa is nothing but m times a, and that is equal to 200 into 0.463, 92.6 Newton. Okay, so the total tractive force required is given by 62.51 Newton plus 29.43 Newton plus 92.6 Newton, that is equal to 184.54 Newton. Okay, so this is the tractive force required to reach 50 kilometer per hour in 20 seconds at a velocity of 50 kilometer per hour. Okay, so at this velocity, what is the amount of power that is required? Okay, so power P is nothing but tractive effort multiplied by velocity, and tractive effort we know 184.54 into 13.89 meter per second, and that comes around 2.56 kilowatt. Okay, and torque requirement will be Ft into radius of wheel. Okay, so 184.54 multiplied by 0.28 will give us the torque 51.67 Newton meter. Okay. Now let us try to compare this thing with the previous, that is constant or linear acceleration. Okay, so whenever we consider linear acceleration, and if we consider velocity as 50 kilometer per hour, then the power required is, see, 3.202 kilowatt, and torque requirement is 64.56. 3.202 kilowatt, and torque requirement is 64.56 Newton meter. 64.56 Newton meter. Okay, you can see the difference. If you are using the second method of acceleration, then power required will be 2.56 compared to 3.2 kilowatt. Okay, so we can see there is an increase in efficiency. Okay, it will consume less amount of power if we initially go at a high value, high acceleration value for first 0 to 10 seconds, and then we will use the acceleration half of the value for next 10 seconds. Okay, then it will consume less amount of power. Okay, so this method is advantageous to us, and this is the reason why at lower speed, whenever we have the vehicle at lower speed, we will accelerate it more, and when speed increases, the acceleration is decreased, and this is how a vehicle is operated, right? So this is the case. Now I have a special case for you where we will consider the same case again, that is second kind of acceleration. Okay, but this time some changes there, right? So what you need to do, I have to reach maximum speed Vf in t seconds. If vehicle accelerates at a rate a for first t by 2 time and at a rate a by 2 from time t by 2 to t, it therefore gives Vf minus V0 equal to a into t by 2 plus a by 2 into t by 2, and that is equal to 3 by 4 at, and value of a is equal to Vf minus V0 into 4 by 3t. Okay, so this is the data available to us, and using this data we need to find the average power, find average power during acceleration and the power required at the end of time t, and the power required at the end of time t. Okay, and you need to compare it. Okay, compare your result with linear acceleration. Okay. So what we have seen in this particular case is the average power required in second case will be 0.667 times the power required with the constant linear acceleration. Okay, so we need to prove this particular thing, right? So let us try to solve this and find out the equation which we already have considered in the example, right? So first, the distance covered is given by s is equal to half at square, right? So if I talk about the first part, that is first 0 time to t by 2 time, in that case let us say we have covered the distance s1, and that is equal to half, acceleration is a only, and time taken is t by 2 whole square, right? So we have a t square by 8. Okay, and v is equal to v0 plus at, a into t by 2. Okay, so what is the amount of work done for this? W1 will be equal to f into s1. What is f? F is equal to m into a. and S1 is already known to us. Okay, so we have m into a t square by 8. This is the work done during first t seconds. Okay, sorry, not t but 0 to t by 2 seconds. So we have this case. Okay, this is my time t, this is t by 2, and this is 0. Okay, and the intended part is to reach the maximum speed vf in time t second. Okay, but we are following this part. I have acceleration a1 a for first t by 2 second, and then my acceleration is half of that of the acceleration in the first t by 2 seconds. Okay, so this is what we are having. Okay, now let us talk about the distance covered during t by 2 to t seconds. Okay, so s2 is equal to v1 into t by 2 plus 0.5 a by 2 t by 2 whole square. Okay, so simplify this thing, we will get v0 plus a into t by 2 into t by 2, just putting the value of v1, plus a by 16 t square, a by 16 t square. Okay, so my result would be t by 2 into v0 plus 5 times a into t by 8. Okay, so this is the distance covered from t by 2 second to t second, and the work done during this time period is m into a by 2 times s2. Okay, so it will be equal to ma t by 4 v0 plus 5a t by 8. Okay, so this is the work done during second part, and this was the work done during the first part. Okay, so let us calculate the total work done. Okay, because we are going to find out the average power during acceleration, and average power during acceleration is nothing but the work done divided by the time. Okay, so let us try to find out total work. Okay, so total work W will be equal to W1 plus W2, that is equal to MA into T by 4 into AT by 2 plus V0 plus 5A T by 8. Okay, so that is equal to MA into T by 4 V0 plus A into T into 9 by 8. Okay, so this is the work done. Okay, so now we are available with the total work done, we are available with the total time period, which is equal to t. So average power during acceleration average power during acceleration is nothing but work done per time. Okay, so now we have this equation of work done where we have the initial velocity v0 also. Okay, so let us consider v0 is equal to 0, the vehicle is at standstill. So if v0 equal to 0, then average power is given by m into a by 4 into v0 plus 9 into a t by 8, and that is equal to m into Vf by 3t into 9Vf by 6. Just putting the value of A. A is equal to Vf by 3. Ultimately, we got M into Vf square divided by 2 into T. Okay. So this is what we are getting. Half Vf square into M divided by T. Sorry. Half into M into Vf square divided by T. Okay. So this is the average power required. Okay. And that is what we have used in previous equation. Okay. So this is what we have done. Okay. You can see the average power required is half times M into Vf square by T. And what is linear acceleration time? Okay, for linear acceleration time, power required is M into Vf square by T. Okay, so that was the difference. Sorry, I have made a mistake here. It should be 2 by 3, I think. Factor should be 2 by 3. 2 by 3 M Vf square by T. And for linear acceleration, the average power required P is equal to M into Vf square by T. So you can see the difference now. Okay. Whenever we use the method 1 of constant linear acceleration, at that time this much amount of power will be required, and if we move on to the second method of acceleration, that is initially we are having the velocity of v1, then we are decreasing it to half, right? Sorry, this is not the exact. If we have the velocity a1 and then we are decreasing the velocity to half, and when we are assuming the constant velocity a, at that time the amount of power consumed will be this much. Okay. So this is the case, and you can see the second method is the clear cut winner. Okay, so this is how we are accelerating our electric or hybrid electric vehicle. Okay, you know now what is the force required to reach the maximum speed Vf in time t second. Okay, so it depends on how acceleration will take place. Okay, so we have considered both the case, constant linear acceleration, and second case where we will have high acceleration when speed is low, and once velocity becomes high, we are decreasing the value of acceleration, and it is advantageous to us, and it will consume 2/3 of the power required in case of constant linear acceleration. Okay, so this is all about the calculation of performance parameter of electrical and hybrid electrical vehicle. Okay, now there is one more calculation which we need to consider is about the battery life. Okay, so once we will go through the energy storage systems of electrical vehicle, at that time we will consider this scenario, that how to calculate the battery life, what is the state of health, what is the state of discharge, what should be the discharge rate, what should be the charging rate, etc., etc., while considering the design of electrical vehicles and of course hybrid electrical vehicles. Okay, so for today we will stop here. In the next lecture again we will start with our motor drives. Okay, we have already covered two kinds of motor drives. One is DC motor drives, another one is induction motor drives, and then we will continue with the permanent magnet brushless DC motor drives as well as switch reluctance motor drives. Okay, so we shall stop here. If you have any questions, then you can ask.